you already see how it fracture, how it become cup and cone. Okay, so you already seen test one question. It's very aligned to CLO, CL1 and 2. So your coming test 2 will be in the phase diagram and polymer ceramic composite. Okay. So today we're still at here. We're still at various failure modes and strengthening mechanism. Again, today is more related to your lab report. Okay, today we look at what is brittle fracture, what is ductile, right? So we look at what is fatigue, what is chip. So a case study here is the Titanic case. Why Titanic can sink or during their venture into the Pacific Ocean. Then why it knocked the iceberg and then it can sink, right? Because in normal logic, steel is very hard. But how come when it knocked the iceberg, it can split into two and so on? So the Titanic case is because of the material in that era. The material science is not yet matured. They just use any metals and then they fabricate the ship. So they do not have a detailed study on what happened if you have a different temperature. So when the Titanic, this ship sailed into a very cold weather, something happened to the metals. It become brittle. Okay, become brittle. So that's why the accident happened. Okay, why the accident happened. Another case is this aircraft. There is a you see the fuselage here, the body. Fuselage means aircraft body. It peeled off in the midair. Okay, why can this happen? Because when you fly at a certain height, outside is low temperature, low pressure. So low pressure, our body cannot sustain, and then high pressure, low pressure also means low oxygen. So how you maintain a very comfortable environment? So when the aircraft climb to a certain altitudes, the pilot will turn on a pressurization mechanism. It will pressurize the cabin. So it means sometimes if the pilot forget to turn on the pressurization mechanism, you will feel very pain when the aircraft climb, especially when they take off. You will feel very pain. If the pilot accidentally turn off the pressurization mechanism, means it will pressurize the cabin up to 1 atmosphere pressure, maybe 1 point something. So means the inside pressure is pressing out the structure because outside is low pressure. So it pressure out. So actually the whole body expand during the whole flight. Okay, so we see this coverage one. Okay, so important is we want to find how things fracture. Okay. So what is failure in material science or in your design? What is failure? Means if the object or the material unable to do the function, if the material you want to hold the tension, but it unable to hold the tension, means it's failed. Right? Meet performance criteria, although it may still be operational. Performance criteria means able to withstand a certain range. Means if you plot the tensile graph, is still maintained within the elastic region, for example. Perform safely and reliability even after deterioration means when you inability to perform safely and reliability. So we don't want to see objects snap. You need time to react when things fail. So this one, so this one you read lots of theory, lots of theory. Okay, so this is what you see in your experiment. This behavior you see is cup and cone. Why the word cup and cone? Cup means it's a cup shape. It's a cup shape. Cone is like that cone. So cup and cone. This one happened in the ductile material. So you see ductile fracture. Most of the metals will behave ductile fracture because I think all the sample you can see when you join them together, you will see there is a reduce of area in the center. I think one of the metal you don't see very roughly where you see a very flat surface. I forget which one is it. Right, there's one object So aluminium is a more obvious one. Right, so it's called ductile fracture. And then what called brittle fracture? You will see this kind of flat surface. It's called brittle fracture. Okay. So the key word, if the question asks you to differentiate between ductile fracture and brittle fracture, the keyword here is slow crack propagation for brittle. For ductile, rapid crack propagation is for brittle fracture. So put this discussion in your lab report. Okay, put this keyword and then discuss how the object behave when you add on the stress to the end of the sample. Okay. So you have this one is after extensive plastic deformation. You have ABC scenario. So A, if you see a cup and cone, or in this case is cone, you do not see cup, you see a cone. So this is highly ductile fracture. If you see there's a teeth, a saw, sharp edges, this one is moderate ductile. Why moderate ductile? You see there's a reduction of area here. If you do not see any reduction of area straight away, flat, like a glass or so it's called brittle fracture. Brittle fracture without any plastic deformation. Without any plastic means there is no reduction of area. Okay. So sometimes the question section A theory part, you ask you to describe or illustrate with diagram on how illustrate with diagram on high ductility fracture, moderate fracture, and brittle fracture. So you draw these three diagrams. 2 mark, 2 mark, 2 mark, 6 mark. Okay. So this is some theory part some theory part. So what happened when you have a plastic deformation? It will start from the center. Okay. There will be a stress in 3 axes, X, Y, and Z. When you have a tensile loading, tensile means pulling at both ends. Then there will be 3 stages ductile fracture can happen. Means the process, how ductile fracture can happen. There are 3 processes. First, specimen will form neck. First will form neck, reduce in area. Then cavities will form. Okay, it will reduce area. Then cavity. Cavity means small hole here. It's like a bubble. Okay, it means there is a, if you look, we study how the molecule arrangement, right? So the sphere arrangement already move away already. So when the 2 sphere move away, there is a cavity, there is a defect there. Okay, so it changed from point defect to line defect to volume defect. This volume defect already. Okay, so form 1 cavity. So in this case, cavity in the neck develop into a crack and in the direction of perpendicular to the applied stress. This direction of crack is perpendicular because the crack is moving to the side. If you pull, so the crack was moving to the side and you're pulling at the perpendicular distance to the crack. Okay, so the highlight one is important. All these keywords, when you explain how fracture happened in your lab report, please include this one. Okay, please include this one in your discussion, how the object failed. Okay. Then after that, when you have a crack happen inside, the third phrase is failure. So crack near the surface already means it reached the surface. Then the crack direction will change up to 45 degrees to the tensile axis and cup and cone fracture results. Okay, so initially cavity happen, then it go perpendicular to the force. Then when it reach the surface of the neck, it will change direction to 45. Then that's why you see cup cone behavior. On the top is cup, below is cone. That's why cup and cone. Okay. Fibrous means fiber, like sharp corners, like bubble gum. If you pull bubble gum, you see there's like a fiber come out. Okay, but in steel is you only see sharp teeth. So you see this one under microscope, you'll see what happened to the surface. Okay, so this week you need to go to lab, go to the another side, right? Fab lab side, go there and do lab. Okay, so this one is a video of how brittle fracture happened at the center plate, 1 mm thick aluminum alloy sheet. This one observed under NDT. NDT is non-destructive test. If you're interested in testing material, one of the area of the work you can study or work is go for NDT tests, NDT test expert in material. So that also very high demand. NDT means you do not destroy the sample, but you able to get what happened to the material. It can be used X-ray, it can use ultrasound or things. It's very popular area. So if you're interested in material, we can go to that. Also very high paying job also. Okay. So you see how it works. You see material. You see the cavity. You crack from the left to right, and the direction is perpendicular to the load, the tensile loading. Okay. So this is how you work lah. Okay. So this one also you've seen axle shaft, that the machine that rotate in the lab. That one is for the axle shaft design. So this one because of overloading of torque. This one you see the small line here is because you already over twist it already. So this one happen in automotive or any shaft. But nowadays material science already very advanced. This kind of case is rarely happen, especially nowadays already have a EV vehicle. You don't use shaft anymore. Okay. So this coming experiment, you look at hardness of the material. This okay, brittle fracture, you look something like this, right? So you have seen in your experiment also. So the brittle fracture, the way it fail is in the cleavage plane. Is in the plane, in the plane. Under normal stress, normal to the cleavage plane. What does it mean? So this is a cleavage plane. You apply stress like this, perpendicular to the plane. Okay, this is a microscope presentation. So highlight HCP. HCP, they commonly show brittle fracture. Okay. This is important when the question go into the chapter 1, chapter 2, chapter 3 crystal structure kind of things. So you have the same HCP question in your test 1. So yeah, then the rest is PCC, this one. PCC, this one you read. This one also some observation. This one is a V-shape chevron marking. Chevron. You see the V shape. This one is the V. And then this one is the source of how it fail. So when brittle fracture, they will have an impact focus point first. Then you see there's a line like sun ray. You see a line of sun ray or a line of like tree roots like that. Okay. Or this one, when you if you have time, you go to those repair car, the front mirror one, the front mirror car front mirror. Those people exchange the crack in the front mirror. You can go and see lah. The grass one is quite obvious one. This one brittle fracture. Okay, so all these are information. How it happened. So because of this grain things. Okay, grain, and then between grain got space there, so it will crack lah. Along the grain boundaries. Okay. Okay. So this one, you know that the direction of force already is perpendicular to the how it cracked. The force is like that. The rest you read. I want to introduce you to brittle fracture also have process. They are transgranular. Transgranular means it's focused on the grain already. This one is a brittle fracture. Just now it's a plastic. Plastic one got cavity, then start to grow, then fortify fracture. But this brittle one is between the intergranule, got 3 stages. You need to mention the slip plane, then micro crack, then energy and propagate, and so on. So this one you read. Important word is you need to always use the granular or intergranular for brittle fracture. Okay, then you draw something like this to illustrate what you are saying. Okay. Okay, now we focus on the things that we can ask you in the test or final exam, because there is an equation. Okay, now how things fracture? We use a sample, a plate here. So stress concentration, fracture of metal. So you will see if things happen, we will define where is your source. There are 2 types of source. One at the side, it means the side there is a stress concentrator there. So either the question give you the problem from the side, or they give you problem from the inner. There's a cavity happen. Cavity is 2A. Remember, when you do calculation, when the cavity one, you are calculating 2A and not A. You need to read carefully the question. It will tell you the stress concentration is at the edge. Edge one, you use A. And if the center one, you need to multiply 2 when you find the final answer, if it's at the center. Okay, I will explain. So this one, if you apply for the stress, this one. So at the side here, you will start from 0. I start from 0. Then when you reach here, you reach the maximum stress at M there. maximum stress. So stress is a concentrator. This will make the thing expand along the x-axis or x-plane. Okay, so you see the graph is in a parabolic shape. Then there's nothing here because got hole here. Okay, the rest you read. Just want to mention the equation here. So how to find the maximum stress or stress concentration at the edge of the hole, or edge of the edge here, the hole lah. We could say just use the word hole, or the fracture or defect, or stress concentration, the maximum or sigma m, given by this equation, occur at the tip, crack tip, and can be approximated by this one. Sigma m equal to 2 sigma o. Sigma o is the nominal stress just now. This one, nominal stress, means the normal stress that you observe in the surface. Usually question will give you a nominal stress. Then bracket square root, this is square root, 1/2 is square root. A divided by rho t. Rho t, rho here is the r or radius of the curvature. This is the rho of the curvature, means the rho of the hole. This r. Tensile. You will extend to the edge, but the direction is perpendicular to the direction of force, the stress. Oh, okay. So this one is just tell you the stress in this point here. So at the end, if you pull, the stress will be happen. You can measure here, right? So if you pull in stress O or force you apply, the force will transfer to here. But if you go deep into there, the stress will increase. The stress will increase to a maximum where it already failed here. This is the maximum value at the location of the hole there, the edge of the hole or crack. So you see the X and XO, so XO here. Okay. So here you see another side is also from maximum to a normal nominal stress. Previous mechanical chapter is we are using nominal, the one that you calculate in your test one, is nominal. Here, the value will be higher than the nominal. Okay. Okay. What I want to highlight here is there is a curvature radius for the hole or crack, and the A is the size of the length of the ellipse or something like the length of the ellipse or the length of the hole, the crack. Okay. I need to remind you need to depend on the question. Later you see one tutorial question. If it's mentioned internal crack, you need to use the A here for internal crack. All right. Or sometimes ratio will be given. The stress concentration ratio or factor means the maximum stress for the crack divided by nominal crack. We'll give it by KT. So you only need to remember the front one. The rest is from the top. You just substitute. Okay. So today, two new equation, stress M and also maximum stress and KT on the crack. This one is stress concentration. Okay, so another equation is called critical stress that initiate the crack. You pull until one value, the crack start to happen. It's called critical stress. Stress, you put a C there, means this one start to have crack already, or start to propagate. In the brittle, this one is brittle material. This equation that you see is in a brittle, give you by modulus Young. This one, delta Y, is specific surface energy, and pi A. We are not going to develop or derive this equation. You just need to memorize and apply. Yes. No, this one you calculate already happened. You in the question will ask you what is the under this stress, what will be the size of the crack? Or if you're given this crack, what is the expected stress on the object, for example? Okay. Or what is the stress at the tip of the crack? The question will ask something like that. Because if you see this equation, there are 4 parameters that we can ask you. Maximum stress at the tip of the crack, nominal stress that apply on the bodies, on the normal engineering stress. Then A is the size of the crack. So maybe it give you, or initially a crack was found by using NDT method. The size of the internal crack is 1 mm, for example. Okay. The question will give you, it give you 1 mm. Sorry, 1 mm. This equal to 2A. So when you apply this equation, sigma m equal to 2 sigma 0 bracket A divided by rho T square root. Remember the A here is 0.5 mm. When you use the calculation, if it's internal crack, remember divide half when you use this equation, because the internal crack is 2A. So, but in your calculation, you're only using A. So remember to divide half. If the question asks you H crack, or it crack from H, it give you 0.2 mm. Then this is A. Don't confuse between the internal crack and H crack. But still we're using A value. Okay. But usually Kara's mistake will be here. You will straight away use 1 mm, then wrong. Calculation will be wrong. It's not 1, it will be 0.5. I'm writing something on the whiteboard. Okay. The calculation here is using A and not 2A. So you see here, A in my slide here, I write surface crack or half the length of internal crack. Okay, surface crack or half the length of internal crack. Remember that lah. Okay, brittle is given. So you have crack propagation stress, maximum stress, and KT. KT is the stress concentration ratio, which is stress M divided by stress O. It's a ratio. Okay, so you look at how the question asks you. It gives you by one statement. It asks you a relatively large plane of glass. Glass, you know, is brittle. So brittle is this one already. Okay. So brittle subject to a tensile stress of 40 megapascal. You put your answer in Pascal. Huh? So convert the capital M mega into 10 power 6 in your calculation. If the specific surface energy is this one, gamma S, specific energy. Modulus elasticity is given, means E, and surface energy is in joule over meter square. Modular elastic is in gigapascal. Remember to change the giga into 10 power 9 in your calculation. Determine the maximum length of the surface floor that is possible without fracture. It asks you the maximum length of surface floor. So here asks you surface floor is this one, this A, not internal floor. Huh? If you read the question, it mentioned maximum length of internal floor, then you are actually having this case. So at the end, you calculate that after you calculate A for internal crack, you need to multiply 2 for the final answer. But if this example 1 for the surface floor one, you only need to go find the A. Okay, then the rest is just substitution. Okay, so you write the equation. Stress critical equal to bracket square root of 2 modulus Young surface energy divided by pi A. Substitute, rearrange this equation. Okay, pull the square root to the left hand side, you get square. Rearrange it, substitute the value. Careless mistake usually is a bracket square something. Okay, you take out the value, the unit here and there, you arrive at meter. You arrive at something meter. Okay, so here you have A equal to 0.2 10 power minus 6 meter. You can put in mm, you can put in micron. This one is micron. Okay. So if you're not good in prefix, if you're not good in all these small micron and all this, it's okay. You remain your answer is in 10 power minus 6. If you not sure, then don't use. If you use, then you're wrong, then wrong answer. Okay, so this one quite direct lah. Quite direct. Okay. Next one is brittle because of defect. Okay. So why metal fail? Because there is a stress razor. Stress razor is a defect location. So if you look at this diagram, you know that this is stress razor location. These sharp corners, it will start from this, and then it will spread to crack. Then the whole thing snaps. And it takes experience to detect where does it fail. Okay, it takes experience to look at that one. Okay, transition from ductile to brittle behavior is called DBT, ductile to brittle transition. The rest you read now. Okay, you will do this experiment in next week, not this week. Next week, you go back to the tensile lab, the civil lab there. So this one is very easy. You just press a button, the reading will come up. What does the thing do is that we call toughness test or dynamic, this one impact test. What does the impact test do? You put and then you knock with the hammer. This is called impact test. So what does it do? it will the machine will rotate to a certain degree, stop there, then you press start, the machine will swing the object down, and then the hammer here, this is a hammer, so the hammer will like a Pac-Man game, you will go and knock the object and this one will break. Then the machine will calculate how many joule. Traditional one, if they like your tensile loading, there's a red color arrow, same. But the one where we already managed to get you the new machine. You will be the first batch using the new machine. Your senior don't have lah. Your batch will be using the new machine. Okay. So this is called Chappie test. Chappie is V-notch. There are two type of experiment. If it's horizontal with the V-notch like that and not from the back, it's called Chappie test. Right. So the specimen is look like this. You pre-load a pre-manufacture V-shape of a defect. The stress concentration is here. So you have all the dimension standard already. Okay. Then Chappie is horizontal. You lay the object horizontal, not from the back. Izot is you lay the object like this, the notch is like that, and then you knock from the same direction. Your lab is only have Chappie. We don't have the holder for Izot, so your batch don't need to use Izot, but in your experiment, you need to know how to write the report. Okay. Okay. So you'll see this kind of sample later on. Okay. So you have all this graph lah. So you have energy absorbed increase versus temperature. So if you increase the temperature, FCC metal will be always high, and then low strength BCC will give you a curve. If you increase the temperature, energy absorbed also increase. High strength is also, if you increase the temperature, the energy absorbed will be higher. Okay, so this one is just show you what are the curve, what happened with the Chappie test, or this one is A283 steel. This one you read. Okay, so you'll see this graph in your lab sheet, in your lab handbook. So this one, you see the energy. This one is in imperial. This one is in joule. So left hand side, right hand side. We are using the right hand side. Same thing. It's just that we are using joule unit SI. Right. Then the temperature here got two axes. One is Fahrenheit. One is temperature. So we are referring to the top. So our lab will be around 25 degrees C, or sometimes quite hot, you can go to 28. So we'll be here. You just read the energy here and there. This one is on the anode steel. We're given 4 samples to knock for Chappie test. Then you compare the value by go to the encyclopedia online, you search, and then you compare the results, whether correct or not. Okay. This also another chart for this one for steel. Okay, steel. This one already seen, Titanic. Okay, fracture toughness. This one is already done. You already learned this now. So you have internal and external. Then use back the equation. So here you'll see that this one is the tip of the peak just now, either here or here or here. You'll see that the stress at the tip will be very high. Then if you move away from the tip, it will go to the nominal. So you have 3 mode of crack. Mode 1, mode 2, mode 3. So what is the mode for Chappie test? Mode 1 is like you tear the thing. Mode 2 is shear. You push it. Then this one is like, C is tearing. So what is the mode for Chappie test? Chappie test. What is the mode? 1, 2, 3. How's the opening behave? V, when you knock, like that, right? So, mode number, which mode? Mode 1, you open like that, right? So like that, mode 1. So discuss this one in your lab report. Okay. So in test, you'll be given one value of mode 1 testing. Mode 1 means you have a K value here, stress intensity factor K. If you look at K1 means it's opening like that. You see K2 means opening shear. You see K3 means like that. Pairing like that. You look at the direction of the crack. So this one, you pull, the crack is going in. This one, you shear, the crack is going in direction. Here also, you peer left, right, but the crack is perpendicular to the plane. This one, mode 3, perpendicular to the plane. It's only the direction is a bit different. So given you by stress concentration, K mode 1, Y shear high A. Y is constant. Usually if Y is not given, you in your answer you just write assume Y equal 1. If the question doesn't give you Y, you in your answer automatic you write assume Y equal 1. You get 1 mark for this one. For assuming. Means we able, when we mark your paper, when you write assume Y equal 1, means you have a higher level of intelligence compared to other students. Means you're able to assume things or predict things. These are the degree level kind of question. Want to see these kind of things. You assume things, you predict things to happen. You can see what does it behave. This one. Okay. So A, again, A, it can be surface or half of the internal crack. Internal crack is 2A. So when you use A, remember, where does it happen? Either at the surface or at the inner. This one. Okay. So the rest is substitution, nothing happen. Another one is you add a C there. Okay. When you add a C there, it means it's a critical already. Critical means the failure of plane is that will be it will cause it to fail. It caused it to fail. So we have K1 and K1C. This one is failure already. It caused it to fail. If the value is below KIC, what happened? If the value below KIC, the object haven't failed yet, but the crack is start to extend already. Because here you are using A there. This A. A means the crack length. It already start to happen crack already, but haven't failed. But if you use KIC, means the object will fail already, means will fracture already. Okay, and remember, you see what is different from the previous one. KIC, you see KI, you use the stress value, the applied stress, nominal stress. Here, this one is what you apply on the object. But KIC, you are using failure stress or fracture stress. Y sigma F square root of A. So this one is failure stress. How you find the failure stress in your test one, you already know you are asked to plot the failure stress. This one, this point. Okay, so don't use the wrong value. If the question asks you Ki or K type 1 crack propagation or mode 1, then you use the applied load. If the question asks you, or you see the question give you the failure value already, it give you a failure stress, then very high chances you need to use this equation. Okay. The unit for KIC is megapascal square root of meter. The unit, this one, unit for KIC. If the question asks you KIC, your expected answer will come with this unit, megapascal, because Y is a constant value. Stress F usually in megapascal or gigapascal. Square root of pi is a constant value. A is in meter. So you can write in gigapascal is okay. Why megapascal here? Because most of the chart that you refer to is in megapascal unit. Okay, so these are the things that in the lab test or something, but you didn't no need to use this one. So it just tell you how it used. Okay, base dimension, thickness. Base dimension of specimen must be relatively large compared to the notch depth dimension A, so-called a plane strain condition prevail. This one is to how to set up the specimen. You don't need to, this is just more on the design question. Is 2.5 the B, the specimen thickness, when you need to conduct a test for this failure, the thickness of the specimen will be 2.5 bracket square of your IC divided by U strength. Okay, in your lab report, you can discuss about this one on the impact test, Chappie test, whether the dimension makes sense or not, something like that. Okay, you can go deep into that. So you see, this will be the standard table you see in the assessment or test 2 or final exam. You see the KIC is in megapascal, square root 2, U strength is given. So you can calculate the A will happen if you're given a certain material. Okay, Y again, Y here, if the question didn't give you the Y value, it's actually is a bonus mark. If you write assume Y equal 1, get 1 mark. Okay. If the question give you Y, then no need to assume lah. So you read from here, either which material is used. Don't read the wrong column. Okay, don't read the wrong column. One is imperial. You just look at the unit SI. Okay, lower fracture toughness is tend to be more brittle, whereas those higher KIC will be more ductile. In final exam, you arrive at two material. I'll give you material A, material B. Apply at the same load. Material A and B. Same stress, but you should know how to convert stress. If you give you the force divided by area of the specimen of this area is the area. Force divided by area, you get stress. Huh? So you compare, then you calculate the KIC. So it tell you apply the same stress, uh, apply the same stress, but give you different A. So you're able to find the KIC value. Right? It will give you failure value. You need to calculate, or from the table, you calculate the A. Then from the A, you able to find your KIC. Material A, material B, you have two numbers to compare. So you ask you which one is more brittle, which one is more ductile. So if you make comparison, you will say according to this statement. Okay, so you can see KIC for aluminium and titanium. Aluminium is 20 something, titanium is 55. So which one is more brittle? Which one is more brittle? Which one is more ductile? Aluminium is more brittle compared to titanium. Okay. Or another way saying is titanium have KIC, means titanium is more ductile compared to aluminium. It's the same meaning. Huh? Same meaning. This is another table. Same material, yield strength, and KIC. Only the position is flipped only. So you either seeing this table or this table in the test. Okay. Then look at the KIC value. Then you describe which one is more brittle, which one is more ductile. Okay. So there's appendix B in the canvas. Go and see, because the appendix B, table B.5, this one you will see in your final exam attachment at the back of the appendix. Get familiar lah. Get familiar. So this one I just write there. Exam or test will be using value from appendix B. Go and canvas and download lah if you haven't downloaded. Okay, so this one you see how you apply. You're given a plate with 207 megapascal stress in tension. So it's a tensile test, tensile loading. If aluminum alloy is used, what is the largest internal floor size? It gives you the A. That this material can support, use Y equal 1. Okay. So if this question do not bracket Y equal 1, you need to assume Y equal 1, you get 1 mark. Okay. So write the equation. KIC equal to KY sigma F square root pi A. This one you refer to this table. Aluminium 204, T5A. So KIC is 26.4 megapascal. In megapascal. What else? Y is 1. Field strength is 455 megapascal. So you're using here, right? You're using here 455. Okay. So you're calculating A. You're calculating A. So you need KIC. You need failure stress. Okay. Sorry, mass support. Okay, mass support. You don't read the yield. You read the 207. Because here is the maximum it can support, but this is the design problems. He asks you the operation must able to support 207. So you need to find the the largest crack size under this load. So don't confuse with the yield strength value in the table. Okay. So the size will be 5.8 micrometer. Mm, sorry, not micron. 5.18 mm. Okay, so this one is edge or internal. The question asks you largest internal floor size. So if you answer stop here, answer wrong. You stop here, you only give half of the internal crack. You need to multiply 2. So this is how you apply the equation. If the question changed to largest surface floor size, then you stop here. If the question like example 2, he asks you to calculate internal floor size, then you need to multiply 2 for your answer, final answer. Yeah, so this will be the careless mistake lah, usually. We go for another 10 minutes, then we stop and call it a day. Okay, so fatigue material, sometimes you can do cyclic stress. Cyclic means you continue to load it. Load, then release, load, and then release, load, and then release. Okay, it's called dynamic test or cyclic test. Okay, so this is also some of the things that you can observe on the surface. This behavior or this presentation is called cram shell. If you go to the beach and you collect cram shell, it will be the shell shape lah. You see the line here like a clam shell. So you can see this is like this is a key, the round shape of key, the old type of key like the marker pen. Right, you put in there, you slot, you have the slot, and then you turn the thing. So this is a keyway. This is a lock lah. This is a lock, and usually it fail at the origin here. So you'll start to propagate. Okay, start to propagate. And final fracture is here. For this module, I won't ask you to do forensic analysis. I won't ask you to draw the prediction of the development of crack. I won't ask you that. Unless you take the material science, then I will ask you that. But for this module, I won't ask you. Right? I'll ask you more on the equation and all this. So these are the sample under microscopic, under SEM. The rest you read. This one also you read. So from here, if you look at this diagram, you know that the fracture will start from here. Okay. Region of crack, so it will spread. Okay, so this one you already done, this experiment. But we have a different setup lah. You have different setup. So your weight is 200 Newton. Pull the object, then you turn it. So you get this cycle. So for your lab report, you go and find this chart, this table from the encyclopedia or material encyclopedia, or test this one. So this one is stress versus number of cycle. So stress versus cycle. This one is in megapascal. Yours one is very low lah. Your one is in Newton. So you take Newton divided by the area of the specimen, you get stress. Right? So you can compare lah. But this one is only aluminium and steel. Okay. So you read lah. Cyclic test. So cyclic test means you load it, then you continue a cycle. What mean by cycle? From this point to another point, this is half cycle, another half. Okay. So you have tension and compression. If you have positive value of stress, means force divided by area. Positive, why? Because the direction go up positive. So you get tension F divided by A positive. Compressed means the arrow is pointing in at both ends, it becomes compressed. So you have full cycle from here to here, amplitude maximum. Okay, so you have this graph. I want to lead you to one equation. So you have a waveform. Sometimes you can push the dotted line above by having tension all the time. It just increase the value of tension. Sometimes you get this one, random stress like earthquake. Earthquake, you do design for earthquake, you need to test something like this. Okay, so this one, if you get a curve, a frequency like this, the mean for stress is get the maximum divided by plus the minimum, get the half. This one you know lah, so to get the mean, take the maximum plus the minimum, divide by 2. Range is from start to end, one cycle. So range of stress is the difference between max and min. Take this one, divide by this one. So you need to depends on the graph. Depend on the graph given. So this one is start from 0. You have tension, compression. The same equation will be applied to this one. This one is above the 0 line here. Okay. So nothing complex. Amplitude is half of the frequency, half of the circle, 0 to 0, half cycle. Range divided by half. Stress ratio R is minimum divided by maximum. You take minimum divided by maximum is the stress ratio. Okay, this one for your info, I won't ask you. Just go and read how crack propagate in the ductile material. I won't ask you. Slip groove is how metal slip in a very smooth surface, how it propagate and all this. It's called slip band crack growth. Again, I won't ask you. This one is crack growth in a high tensile stress. You see it behave like shell. Ultimate, this one you read now. Okay, this one for your lab report also. How it will affect the fatigue strength. First, stress concentration. This one you need to discuss a little bit for the machine one. So this one with fillet and without fillet. This is how you improve the design. Reduce the stress concentration by having fillet. Surface toughness also. Why surface toughness? Because surface toughness is actually how smooth is your surface. Right? How smooth is your surface? If your surface do not smooth, actually there is a sharp like a zig, like a saw. If you look under microscope, it will be like this. So all these sharp, there is a stress concentration here. There's a stress concentrator at the tip here. So this one will form A. This will be your A. So that will like one you calculate KIC, all these things. Okay. Surface condition. This one is on the strengthening. So you see all these have got strengthening, so it become more and more strong. This one you read. So this one is design. How this is the mechanism, the spring for the big lorry. You see under big lorry, old design. You see this three plate where they can go up and down. It's like a suspension for the old design. Nowadays, all the big truck also using this one. See, before shock cleaning. Shock cleaning is surface treatment for.
The critical area of a commercial vehicle spring under high load is its surface. Even minor flaws in the surface layer can create starting points for cracks. This, in turn, can lead to spring fracture. Usually, at the worst of times. To avoid such a situation, we at Schulmecker treat the surfaces of our springs with shop peening. This process ensures a more homogeneous surface and creates a residual compressive strength.
Particles to smooth out the surface, to reduce the stress position.
To come to full effect, this residual compressive strength has to penetrate the surface to a precisely defined depth. This can be checked with an X-ray diffractometer, a test that's carried out as a standard at Schulmecker. That's why it's not just a piece of good luck that Schulmecker springs have a much longer life. A longer life means more safety. Schulmecker springs, quality from the technology leader for safe arrivals.
Environment, corrosive environment, and all this. So this is a fighter jet. So if the fighter jet is always flying at the sea coast, especially those Marine Corps or Marine TUDM in Malaysia, right? Tentera TLDM, Tentera Laut Diraja Malaysia. They have a wing also. They have a means they have a unit of air unit. So they always circle around the borders. So these are the things that will corrode things lah. So you take corrosion module in the Dr. Yuli class. Maybe in future there's an elective, right? So these are the things lah. So this is fracture toughness. So this is how people do lah. This one you go home and see. 1 minute, 2 minutes. Okay, 2 minutes. So there's a grip there. Lots of sensor. Extentometer is to measure the expansion. You see the crack. This is the dynamic test. Load and release, load and release, load and release. So for so many times in the high frequency. This is a pre-crack. So the back is a test engineer who is also in a very high demand. This one you read. I want to so you read. Okay, so this one is how the crack under cyclic test. At the end, you are using this equation. Remember this equation can already. It's actually y equal to mx plus c. Y is, you're given a graph. On the left or right is dA in the log form. This one. So log something. This one is 10 power something. So you convert into log. M is the gradient. X is delta K. Plus log A is the intersection of that point. So you have 3 region there. You go and read lah, this one. At this semester, I don't think I will ask you this. So this one is your info. But if this one come out, I will let you know lah. Okay, example 3, go home and see how you use the equation of this one. Just go and read an application of log and this one. Read. I think we stop here now.